Okay, now we are going to do the velocity of sound in air determination practical. But before doing that, I should just discuss this experiment number 13, which I haven't put into my notes. Like, this is also the same thing. I mean, like the 12th practical, where we were able to find, uh, we were able to use the sonometer box and find the unknown frequency of a tuning fork. Likewise, it's the same apparatus in this practical. But the thing is, in that practical, okay, we changed the mass which was hung, and then accordingly we calculated the length of the sonometer wire. In this practical, what we do is we are keeping the same mass, okay, but what we are doing is we are going to change the frequency. Like if we put 100 hertz, what is the length we get? If we put 200 hertz, what is the length we get? Likewise, we are going to change the frequency and look at the relationship between the frequency of the tuning fork used and the length. Okay, and then like it's the same equation, right? This capital T does not change because the tension will be the same since we don't change the hanging mass. Okay, so T over M will be a constant, and we get a relationship between L and F. Okay, this is just to verify that relationship. It's nothing like there are no points that you should remember about this practical, but just remember that there's a practical like this as well. Okay, the earlier practical is the most important part. From that, if you get the concept by watching the earlier video, you'll get this. Okay, but in this video, the main practical which I'm going to discuss is this one. Okay, how we can determine the velocity of sound using a closed resonant tube. Okay, and also determining the end correction. Right. Let's look at it like this. Now, in the earlier practical, what did you do? Hmm? We used a certain tuning fork, and we related the frequency of sonometer wire, and then we got the expression for this for the frequency of the tuning fork, unknown frequency. All right, using a graph we did that. Here, what we're going to do is something similar, but this time over, what are we going to do? We're going to take a tube. Okay, I'm going to only tell the theoretical points now, right? Which is there's a beaker like this. Okay, there will be a beaker like this, and there will be a certain amount of water in this tube. Okay. Now, if we keep a tuning fork like this here, what happens is it will form waves. Okay. It will form uh, a sound wave. Now, this is an open tube, right? Okay. So this is a closed tube, not an open tube. So it will form overtones like this. What we do is, first of all, like we are expecting the fundamental overtone to be produced. If not, when the fundamental overtone is produced, we are going to calculate the length. When the first overtone is produced, we are going to calculate the length. When the second overtone is produced, we are going to calculate the length. Likewise, we are going to plot a graph. Okay. Now let's see. Now this is the fundamental overtone. Okay. Or the first harmonic. Right. So here if we say this is L, we can say L is equal to lambda divided by 4. Therefore, we can say lambda is equal to 4L. Okay. And V is equal to F lambda. Right. I can say F is equal to V over 4L. Sorry, the other thing, I mean, I missed a point. Now, in these tubes, right, since we don't know exactly where this ends, we are going to take a end correction called E. Okay, here we are going to take that end correction, right? So, we can say V is equal to F times 4L plus E. Okay, so F is equal to, we can say like this. Yeah. We can say F is equal to V over 4 times L plus E. Okay, you can say F is equal to V over 4 times L plus E. Okay. Um. No, like we'll now it's like this. That is correct. That the expression for frequency is totally correct. But here, what we want is like while we change this respective uh, overtone, whether it's a fundamental first or second, we are going to observe the length, right? So L should be the independent variable. So we can say V over 4F is equal to L plus E. V over 4f. Okay, and we can say L is equal to V over 4f minus E. Okay, and this is the first fundamental auto. If you look at the second auto, right, something like this. Okay, so here we can say 3 lambda by 4 is equal to L. Therefore, lambda is equal to 4L by 3. Okay, it should be actually L plus E, since we are going to get the incorrection as well. And we can say, look at carefully look at these derivations, and you can also try it again. Okay, V is equal to F lambda. So V is equal to F times 4 over 3 L plus E. Now I'm going to subject L. I can say 3V over 4F is equal to L plus E. Therefore, L is equal to 3V over 4F minus E. Now we got this as well. Okay. Now let's try to do one more. So it be something like this. Okay. Don't worry about the diagram. So here you have 5 lambda by 4, because you have, this is lambda by 4. 1, 2, 3, 4. 5 of them are there. Okay, there are 5 of them. 5 lambda by 4 is equal to L plus E. Lambda is equal to 4 over 5 L plus E. V is equal to F lambda. V is equal to F times 4 over 5 L plus E. So we can say 5V over 4F is equal to L plus E, and L is equal to 5V over 4F minus E. We got 3 expressions. First one this, second one this, third one. So you can see there's a certain pattern. See the number. Here the number is 1. Here the number is 3. Here the number is 5. So what can you say about that? See, first of all we got E over V over 4F minus E, right? V over 4F minus E. Then we got 3 times V over 4F minus E. Then we got 5 times V over 4F minus E. So if you just consider these numbers, this 1, 3 and 5, they are according to the arithmetic progression of 2n plus 2n minus 1. Okay, 2n minus 1. Right? If n is equal to 1, 2n minus 1 is 1. If n is equal to 1, 2n minus 1 is n equal to 2n minus 1 is 3. n equals 3, 2n minus 1 is 5. Okay, that is according to that arithmetic progression. So you can say finally, okay, L is equal to K times, okay, you can say this as a constant. This V of f is a constant, okay, times K minus E. Okay, so this is Y equals mx plus C time. Did you understand this? Right. Our independent variable is K, which is actually equal to 2n minus 1. Okay, which is actually equal to 2n minus 1. Okay, 2n minus 1. This n is what? N is equal to the nth harmonic. Hope you understood this. Okay. Yeah, there's a little bit of stuff about this independent variable. That's the only confusing thing if it is going to get confused. But if you learn it properly, that's fine. Okay, here we have the graph. Our independent variable being K and our dependent variable being L. All right. Dependent variable is simple L. Independent variable is capital K. But capital K is actually equal to 2n minus 1, where n is the number, like the position of the harmonic. Okay, if it is the first harmonic, simple n is equal to 1, and capital K is 2 times 1 minus 1, which is equal to 1. Okay, so when you plot the graph, what you do is, for K is equal to 1, we calculate which value. For K equals 2. K equals 2 means what? K equals 2 means which harmonic? If you take the, if you take the second harmonic, what is the value of K? If you take first harmonic, K is 1. If you take the second harmonic, K is equal to 3. See, this value is K. So we get the next reading for 3. The next reading for 5. Likewise, we'll get a nice graph. Okay. Hope you understood. You should understand how these independent variables and dependent variables work together in the system of equations, right? So after plotting this graph, we can get the gradient as V over 4f. So velocity of sound, what is the velocity of sound? 4f multiplied by the gradient. Okay, because in this practical, we are using a non-frequency, we are using a non-tuning fork. Okay, right. So I hope you understood it. If you have any doubt, go back and refer the video once again. Okay, right. So now let's look at the points. So this is what I have said. See, we get the final equation. L is equal to P over 4F multiplied by K minus E. Okay. And the other thing is, what about this minus E? Now, to draw the graph, actually it should come like this. Okay. You get something like this because you have a negative y-intercept. And let's say here you have a value called minus 2. Then the end correction is equal to 2 meters. So whatever the unit you use. Okay. Right. So we can directly say the y-intercept is equal to the end correction. And uh, the gradient is equal to V over 4f. Therefore, we can say V is equal to gradient multiplied by 4f. This is what I told earlier. And E is equal to the y-intercept, value of y-intercept. Okay. So this is also like do this derivation twice or thrice. Do in a paper. Okay. Then only you will understand, remember this properly. Right. Yeah, you should logically understand how these equations come into this format. Okay. Right. Let's see. Due to practical difficulties. Length of resonance is very large. It's true, right? Now, for the first harmonic, it might be okay. For the second harmonic also, it might be okay. But what about the third, fourth harmonics? The length will become much larger. So you might have to use a longer tube. Okay, that might be somewhat difficult. It is very difficult to identify the resonance state of second overtone because of very low intensity. Now that is very important. Okay, like in the earlier practical, in the sonometer wire practical, I told you that now they can ask a question like, why do you use fundamental overtone? Like in that practical, we always start from the minimum length and separate the bridges to ensure that we won't miss the fundamental overtone. The reason for using the fundamental overtone is because it produces a very high sound intensity. Fundamental overtone produces a very high sound intensity. But when you go higher and higher, like the second overtone, third overtone, those things produce a very low sound intensity. So in this practical, actually, if you want to plot 5 points, okay, if you want to plot 5 points, you should take the fifth harmonic or the fourth overtone. So the sound intensity produced in that overtone will be very much lower. Okay, so things are not going to be easy, right? So that, I mean, this practical is not actually practical, right? It's sort of impossible to do accurately. Okay? Determining velocity using a closed resonance tube and a tuning fork. That is very not this practical is not very practical. Okay, but if you go to the next practical, you can see like using that practical, we can easily determine the velocity of sound in a much more practical way. Okay, since this practical is not practical, we have a lot to talk about this, right? Difficulties, improvements, likewise, we have a lot to discuss about this practical. Okay, and you should know how the derivation comes. What is the correct procedure to obtain resonance states and why? Start with the lowest length of air column. This thing you know, right? Even in the early practical also, we started with the minimum length between the bridges so that we did not miss the first fundamental overtone or the first harmonic. Okay, so it's the same thing here. Right? That is to make sure we get the fundamental node at first. Two readings we take in this experiment: scale reading at water level, scale reading at open end of the tube. Now this is actually hinged to a clamped to a stand, right? So here to get the actual length, okay, I already explained the theoretical part. To get the actual length of this thing, okay, we should get the meter ruler reading at this point and at this point and get the difference. Okay, these things might be very small points, but please give an extra effort. You might feel like, okay, I remember these things. If they ask, I can answer, but no, like you have time. Okay, spend some time and memorize these questions and answers. That will be very useful, especially to like boost your confidence, right? Okay, because these are the questions that they have repeatedly and repeatedly asked in past papers since like 1997. Okay, right. What is the type of equation we use? So this thing I explained. Okay, this K, right? the constant k is equal to 2n minus 1, where n is the respective harmonic. Okay. That one, if you can't understand again, please refer the video and watch that. What is the type of waves formed here? Surely it should be standing waves, right? That's something theoretical. Write a practical. Yeah, this one is the same as question one. Okay, I've written plus. Okay. I hope you all are okay with this practical of determining the velocity of sound using a closed resonance tube and a single tuning fork. Okay.